Let's understand dropout regularization. But first, why we need regularization in modern deep neural network? If the model is too complex, then it has a tendency to overfit. It tries to learn the every minor details in the training data, which are not even necessary. And that's how it fails to generalize well. So that's why we have so many regularization techniques like L1, L2 regulation, dropout, batch normalization, data augmentations and all. So in this video, we are covering dropout. I'm sure you must have heard about ensemble technique in machine learning. If not, I'm just giving quick description here. See, in ensemble technique, we train multiple models with different data, different architectures or different initialization. Then we combine their predictions, either averaging or taking votes, and the result is we get a better generalization. What we do in test time? In test time also we test on multiple models and then we take average of different model predictions at test time. So if we have k models, then also we'll have k predictions. So let's say y1 hat, y2 hat till yk hat, these are k predictions. So our predicted output will be the average of this k predictions. So dropout takes inspiration from ensemble technique. So there are a few problems also with ensemble technique. Like we have to train multiple models and then at test time also we have to test in multiple models. So it takes lots of time at test time. So during training time, if it is taking more time, that is still okay because we are doing the training once, but we'll test that new data multiple times again and again, right? So at test time, we don't want to test on multiple models. So that is where dropout comes into picture. So dropout is the solution here. In dropout, what we do, we will run only one model at test time, but still it will mimic many models. That's the beauty of dropout. So now understand what dropout does. So this is a complex network. We need a simpler network. In dropout, we get rid of few neurons and associated weights in each iterations. So what are these weights basically? These weights, let's say these WIJs, these define the importance of the neurons in the network, either input nodes or hidden nodes. If this weight value is more, that means these nodes are important. If this weight value is less, that means these nodes are not that important. So in dropout, we are removing nodes along with the associated weights in each iterations. So let's say this is the original network and after removing few nodes, we'll get this type of thinned network. So we can get rid of any non-output nodes with some probability in every mini batch. So and removing nodes means removing nodes with all incoming and outgoing edges. So you know about mini batch iterations, right? So there are, let's say this is one huge data set we have. We divide the data into multiple mini batches. And in each iteration, we update the gradient weights for one mini batch. So this update is basically this gradient update in gradient descent. Wt plus 1 is Wt minus alpha time gradient of this error. Right? So this updates we do for each mini batch. And at each mini batch, we are having a different types of thinned network. So in every mini batch, we might get a different architecture. So let's say this is mini batch 1, we got this type of architecture. In mini batch 2, we got different types of architecture. So that's how it is mimicking, like we are training multiple different types of models in different iterations. So how do we decide which nodes to remove? So we set some probability for that. So let's say we remove input nodes with probability P and hidden nodes with probability Q. Of course, the output nodes will not remove because we need the outputs, right? We can remove input nodes and hidden nodes. we will set some probability to remove those nodes. 0.2 means let's say 20% neurons will be dropped, 0.5 means 50% will be dropped. So you control how many neurons are turned off during using this dropout rate. So now how these weights are updated for each node. So in this mini batch, this is the thinned network. These nodes are present, we can update these nodes, right? But what about this node that is not present? So in every mini batch, we'll update weights only for those nodes that appear in the network. But nodes or weights that doesn't exist in the mini batch will simply retain previous weights. So for this node, let's say whatever the previous weights we had in the previous iteration, that will retain, and that will be passed along to the next mini batch. So let's say if there are n nodes in the original network, we'll get 2 power n network configurations or thinned networks. So if we have that many mini batch also, right? So that is the max number of thinned networks we can get from dropout. Now, what's the difference in training and test time in dropout? In training time, dropout is on, we are removing nodes. Testing time, dropout is off. We just have one network. So we are removing nodes, we are updating nodes that are present there. We are not updating the nodes that are not present at that point. And that's how all the nodes and weights are updated properly. But at test time, the whole network is present. We'll test on this full network one time. So during testing, all neurons are used. There is no dropout. That is the advantage over ensemble technique in dropout. The benefits is it reduces overfitting, it improves the generalization, then it makes the model robust. There are a few downsides as well, because it might be a little bit slower, because at every mini batch iterations we are just removing nodes and then we are training, so it might be a little bit slower. Too much dropout means underfitting. If we remove too many nodes, the model will underfit. So we need to balance how many nodes to remove and all.